Hello everyone, my name is Xiaogang Xu. I'm from the Chinese University of Hong Kong. Here I will present our paper, Text-Guided Human Image Manipulation via Image-Text Shared Space, which is published on TPAMI. This work is driven by the daily life need. For the text-guided image manipulation, users can provide a brief language as a text to serve as a condition for image manipulation. Those conditions always conflict with the content of the input image, which are set to manipulate. Most current workers feel this task in the framework of conditional GAN. For the generator, those methods often adapt encoder-decoder structure. They would first extract features for image and text, and then they fuse image and text features. The most common way to fuse is concatenate, and such features are sent through the decoder to synthesize the final output. And the discriminator, on the other hand, also leads the text as the condition for the input of the discriminator. In this way, the discriminator can classify whether one image is real and fake based on the condition of the text. However, such adversary learning with conditional adversary loss is often proven to be unstable. There are several shortcomings we need to consider for text-guided manipulation tasks. The first one is that when we use text as a condition to manipulate, it is not easy to obey the correct areas to manipulate, since the language is variance in its form of description. The second property of using text for image manipulation, which is not considered by the current method, is that the text is ambiguous in the description of appearance. For example, for this image and its input text instruction, we aim to change the clothes to blue. But what is blue? It can be light blue, bright blue, dark blue, and so on. Therefore, this method should give such sequential results for users' choice, while the current method cannot produce such results. And the performance of text-guided manipulation depends on complete text descriptions, while users often prefer to provide brief text. In other words, we need to disentangle the features to be manipulated from the irrelevant features, which is difficult. Those three shortcomings can be dealt with in our framework. Different from current method, we first project both image and text features into the same feature space and disentangle the attribute space into irrelevant and relevant space. In this way, we can compute the direction of the attribute vector. With different editing strings, we can move the image feature in this shared space. The different movements correspond to different editing strings in the image. In summary, the multi-module manipulation can be decomposed with a unified representation for manipulation feature and the manipulation features in the corresponding shared space. This is the first attempt to implement such an idea. To implement the shared space, we extract the spatial information from the input image, use it as the structure information for synthesis, and embed both image and text features to the shared space, predicting the style information for synthesis. With this shared space, we can utilize the attribute vector for the control manipulation by mapping both image and text features into the shared space that entangles the manipulation direction, which is the attribute vector. Shifting the image feature with the attribute vector and different weights, we can control the strength of editing. And in this shared space, we can use training loss to disentangle the text relevant and text irrelevant attributes to improve the accuracy of manipulation. Our framework is called ITSS-GAN. Give the image and text from the users. We first use offline trained pose estimator to obey the pose of ISP, and ISP are sent to the corresponding encoder to obey the deep feature representation. For the text and the image features, they are sent through the attribute vector estimator to obey the direction of the attribute vector, and the modified features can be computed as the parameter of add-in for the decoder. Meanwhile, the spatial feature fs is set as the input of the decoder to ensure the manipulated output has pose of p. Our manipulation framework is built based on the training of two generation modules to learn the shared space, which is GI and GT. For GI, we extract the features of I and P through the corresponding encoder, and the image feature can be computed as the parameters of add-in to synthesize the target image. The loss is the reconstruction between the output and the ground truth, as well as gain loss. For the generation module GT, the input is S and P instead, and use the feature of S to compute the parameters of add-in. The loss function also includes the reconstruction loss and gain loss. The core problem is how to train the manipulation path GM. First, we need to divide the text input into different categories. The training data in common dataset normally cover all concerned attributes in image, and the content of the text is often accounted with the input image. Such text is called complete and positive. However, users prefer incomplete and negative. So we need to do the augmentation for text during the training. For a complete and positive text, we first need to locate the DOM, and if we transform it, we can embed the incomplete and positive text. Next, we need to locate the adjective, which often describes the value of attributes. We can use a dictionary in memory to search what to modify for this adjective. In this automatic pipeline, we get incomplete and negative text. For the next question is how to embed the pixel level supervision for different types of text. For the positive text, we can use the input image itself as the ground truth. But how about the negative text? We adapt a self-supervised strategy. First, we complete the content of the text, which is incomplete and negative, make it to be complete and negative. SN star is in fact describes the target appearance when we use the text as SN, and we then send such text into the module GT, which will output OT. The OT has appearance, which is accounted with SN star, and the pose OP. So OT satisfies our requirements. It can be sent as the guidance for the output of the manipulation module, which is OM. So we can set the learning objective as the distance between the synthesized images with their corresponding guidance. For the output with the input as a positive image text pair, the content should not be changed. So we mention their distance with the input image. Especially, we mention the distance from pixel level to perceptual level. The output with the input as negative image text pairs, the loss is similar. While the distance is mentioned from the synthesized image and the output of module GT. In summary of our method, the overall loss term for the image encode EI, text encode ET, spatial encode ES, network to compute add-in parameter M, decoder D, attribute vector estimate A, and discriminator D are defined in this page. In experiments, we train the two large-scale datasets which satisfy our requirements for training, including CHK, PDS, and Sabri, which has a textual annotation for images. And the matrix includes the VK score that mentions the model manipulation accuracy. The higher, the better. FID that mentions the generated image's quality, the lower, the better. And L1 reconstruction error, which is computed with the positive text to mention the ability of preserving the irrelevant attributes during editing. The lower, the better. It's obvious that our method achieves the highest VQ score, the lowest L1 loss. And we do the ablation study to show the effectiveness of each loss term in our framework. In the user study, we first show participants a set of manipulation results and require them to choose one with the highest quality and accuracy. And in the second user study, we show each participant with the manipulation process and the function of different method, and ask them to choose the best one that satisfies their preference. And since data like face and has identity information, we need to consider the ability of identity preserving. To this, we first train a classifier on the dataset with the real images to classify identify information such as face ID, and then we test the manipulated images whether the output identity of this classifier will change before and after manipulation. The result shows that our framework can effectively preserve the identity information during image manipulation. We also evaluate our framework's performance with more inaccurate structural inputs by adding perturbations to the coordinate of key points in the pose during evaluation. Our method until gave better results over baselines with the perturbations in the pose, showing the robustness of our method. Visual comparisons of the used baseline and our method on CUHK-PDS and Stability are given here. Also, we have mentioned our framework uses the structure of the ADA-in decoder, so we can control the pose of the output through the control of the pose input are shown in this page. And since we use attribute vector in the shared space to edit the appearance, we can control the weight of attribute vector to achieve continuous control for manipulate appearance through text. Those are results on CUHK-PDS and Celebrate datasets, which indicates that it works. Especially such continuous control for appearance editing can be achieved simultaneously with the control of pose. Okay, thanks for your watching.